Welcome to section 11.17, part 5. This is the 125th session of the CISSP exam prep series. This final part explains how a single medium gets shared without chaos. In this session, we'll cover how devices share the wire. We'll answer several questions. How many destinations can one transmission reach? How do networks decide whose turn it is to talk? How do the sensing methods differ? And how do orderly, permission-based methods keep collisions from ever happening? Why does this matter beyond the exam? Because a shared medium is a shared problem. Picture an open-plan office where everyone tries to talk at once in a meeting. No one is heard and the room descends into noise. Networks face the same challenge on a wire, and the rules they use to take turns directly shape performance and reliability. Understanding these methods helps you reason about congestion, efficiency, and why some designs stay orderly while others degrade under load. How many destinations can a single transmission reach? That depends on the casting technology, and there are 5 worth knowing. A broadcast reaches every possible recipient at once. A multicast reaches a specific chosen group. A unicast targets exactly one recipient. An anycast sends to whichever member of a group is nearest or best positioned in the network. And a geocast delivers to every device inside a defined geographic area. The distinction is simply about audience, from everyone, to a group, to one, to the nearest, to a region. Picture a speaker choosing whether to address the whole auditorium, a reserved section, one guest, the closest usher, or only the people seated in the balcony. How do networks decide whose turn it is to talk? Through media access approaches, which fall into 3 broad philosophies. Arbitration uses a central authority or a fixed set of rules to grant permission, so devices ask or wait their turn under coordination. Deconfliction avoids clashes in advance by handing each device its own dedicated time slot or frequency band. And contention lets devices simply compete for the medium, transmitting when they have something to send and dealing with collisions when they happen. The trade-off is order versus freedom. Coordinated methods prevent chaos but add overhead, while contention is simple but can get messy. Think of a meeting run by a strict chairperson versus scheduled speaking slots versus a free-for-all where people jump in. How does basic carrier sensing work? By listening before speaking. In carrier sense multiple access, a host first checks whether the medium is in use. If it is quiet, the host transmits, then waits for an acknowledgement. If no acknowledgement arrives within a timeout, it assumes the message failed and starts the whole process over. The catch is that this basic form does not actually handle collisions. It only notices failure after the fact, when the acknowledgement never comes, and then tries again. Picture someone who listens for a pause in conversation, jumps in, and only realizes they were talked over when no one responds. How does collision detection improve on that? By listening while it talks. This contention method starts the same way, sensing the medium and transmitting if it is free, but it keeps listening during transmission for signs of a collision. The moment 2 hosts clash, the sender broadcasts a jam signal telling everyone to stop. Each host then waits a random interval before trying again, which keeps them from colliding a second time in lockstep. This is the method wired Ethernet uses. It tolerates collisions but reacts quickly, though all that stopping and retrying costs a meaningful slice of throughput. Think of speakers who fall silent the instant they hear themselves overlapping, then each count to a different random number before resuming. How does collision avoidance take a different tack? By seeking permission before transmitting at all. Here a host listens, and if the medium is free, it requests permission to send rather than just sending. Only once permission is granted does it transmit, then wait for acknowledgement, starting over if none comes. Because only one device is cleared to talk at a time, collisions are largely prevented rather than merely detected. This is the approach wireless networking relies on, where you cannot reliably hear collisions in the air. Picture a classroom where students raise a hand and wait to be called on, instead of blurting out and colliding. What makes token passing collision free? A single pass permission. In this orderly method, a digital token circulates among the systems, and only the host holding the token may transmit. When it finishes, it releases the token to the next system in line. Because exactly one device ever holds the token, 2 systems can never talk at once, so collisions simply cannot occur. This approach powered older, ring-based network technologies. Think of a meeting where only the person holding a single talking stick may speak, and they must hand it on before anyone else gets a turn. How does polling keep order from the top down? By having a primary system offer each device a turn. One system is designated the primary, and the rest are secondaries. The primary asks each secondary in sequence whether it needs to transmit, and grants permission when one does, then moves on to the next. It is the mirror image of collision avoidance, where the secondary asks for permission. In polling, the primary offers it. It can even weight the order to give a critical system more frequent turns. Picture a teacher going around the room, calling on each student in turn, and circling back to a key student more often. So let's bring it together. Casting technologies define reach, from broadcast to everyone, through multicast, unicast, and anycast, down to geocast within a region. Media access falls into three philosophies: arbitration, deconfliction, and contention. Trading order against freedom. Basic carrier sensing listens then hopes. Collision detection reacts to clashes and drives wired Ethernet. And collision avoidance asks permission first and drives wireless. Token passing and polling prevent collisions outright through a pass token or a primary offering turns. Choose the method to fit the medium and the shared wire stays orderly. That completes our tour of secure network components. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.